I really want to focus on this one today, and I actually want to build this up from first principles, and I want to do it in such a way that we, instead of starting with this one, which is the most interesting, this is like the Dos Equis, man. It's the most interesting formula in the world as of today's lesson. We're going to get more fun ones later, but today's lesson, this one's interesting, right? What I want to do is actually sip the beer before I decide I'm interesting. So I want to actually talk about some of the prerequisite ideas that go into this, and then we'll build this one up from those prerequisites ideas, if that's okay. All right. With that in mind, what I was thinking is I would like to start with, so let's begin with some beauty, and then rather than a beast. Right? That's a beast. It's not. It's actually quite beautiful when we see it later, but I want to begin with something a little bit beautiful. So recall. Let me ask you this: if I were to take the 2 norm of x squared, how do I realize that as an inner product? X inner product x, and that's for anything on the inside there, right? Okay. I also want to recall, so that's what you might call the inner product realization of the 2 norm formula. This is I might call that the inner product version of 2 norm squared. Okay, let's recall this one too. You might call this thing Pythagorean Theorem. Can anybody remind me what the statement of the Pythagorean Theorem was? And I actually want the full statement, not just the punchline. So you got to set the joke up. What's the punchline of the Pythagorean Theorem? Okay, yeah. Ha 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 ha. That's a good one. A squared plus b squared equals c squared. But that's not the setup, right? What's the setup? Yeah, if A, B, and C are the side lengths of a right triangle, then what do we say? And I actually mean more than that, right? With C the length of what? Hypotenuse. Then what? Then a squared plus b squared equals c squared. Can you draw that in the air for me? Yeah. And my claim is you all use that every single day when you're walking, right? Generally, if I want to get to that seat, I don't go like this. Right? My son and I do that all the time. We play that game together. But normally, normal human beings would just go right to the seat, right? Because the idea is that traveling along the sides of a triangle is more expensive than traveling across the diagonal, right? Okay, so in this situation we have that this is going to be A, this is going to be B, this is going to be C. And then maybe we call this thing right here, I'm going to call that angle theta. And what did you just say about theta? Theta is 90 degrees. Okay, so and remember that C is the side opposite of what? Angle theta. So the length of this thing is the side opposite to that, right? All right, so there's one more piece of information that I need. Then we're going to make sure that we understand all of these things from first principles, and then we're going to develop, Okay, the last piece of information that I need is something called the Law of Cosines. All right, does anybody remember the full statement of the Law of Cosines? You could also give me the punchline if you wanted to.
I think it's a squared plus b squared minus 2ab.
So there's something about a squared plus b squared minus 2 times a times b times cosine of theta, which gives us some hope, right? Because if it's a law involving cosine, we would pray that there's a cosine in it. Okay, anybody else want to help set that up, Chandler? You struggling with allergies today? Oh, just brutal, right? I know that feeling. Yeah, okay, so there's this thing about that this is somehow equal to c squared. Okay, so that's the punchline of that joke, or that theorem. What's the setup? Peter, maybe? Because I don't want to overwork you, Sam, but I know you got it.
Like a rough estimate, if you know the side lengths, there are two sides of a triangle, and then you have the angle which is theta. And you can use A, B, and theta to solve it.
Of any triangle, if A, B, and C are the lengths of the sides of any triangle, and theta is the angle between sides labeled A and B. So then what would that say about C? C would be the side opposite. If theta is between A and B, C would be the side opposite, right? C is opposite side. I think there's a better word for that, of theta. Then that's true. Okay, let's draw a diagram. So this we might call that alpha or theta, sorry. We might call this thing A, we call that thing B, we call that thing C. And then what's the claim of this particular law of cosines? What does it say? That if I want to measure the side, the length of the side opposite, the square of that is equal to the sum of these squares minus something having to do with the cosine. How are these related?
That's the generic.
It's times 1.
If theta is 90, what happens?
Zero.
Yeah, so if theta equals 90, then cosine of theta equals 0, and what pops out? Yeah, so that means that the Pythagorean theorem is the child of the law of cosine. In this case, you just have to birth a 90-degree angle and you're done, right? In other words, the law of cosines is a generalization of the Pythagorean theorem to deal with all possible thetas on the inside. Okay. All right. So those are 3 pieces of information that we're going to need.